Your textbook has some theorems for how to add or subtract two series, given some conditions. I'm going to do this one without those theorems. If you want to look up those theorems, you can, but it feels like kind of plug and chug unless you actually do the proof. But this will help us when we get to Taylor series too, expanding things, rewriting them, writing them as a new series. So let's look at this one, and we could apply the same principle to the second series they're asking us for. This is 1/2 times f of x. Let's look at some of the partial sums, okay? Let's look at what happens when we plug in n equals 0 into both these sequences. So if you plug in n equals 0, then x to the 0 power is 1. 0 factorial by definition is 1, so this would be 1 plus g of x. If we plug in n equals 0 there, that's this is the 0 power, so that makes 1. This is 1, so it's going to be 1 plus 1. Okay, so all I did was I just said, let's just take this one step at a time. Instead of trying to go to infinity, let's just do n equals 0. And now let's do n equals 1 and see what our expression turns out to be. If you plug in n equals 1 in for f of x, then you get x to the first over 1 factorial. But if you plug in n equals 1 into g of x, negative 1 to the first power is a negative 1. So this is negative x to the first over 1 factorial. And then if you plug in n equals 2, you're going to have x to the second over 2 factorial plus, now this isn't going to be plus and negative this time because negative 1 to the second power is a positive 1. So this is x to the second over 2 factorial. So this term, nothing's surviving, right? They're perfectly canceling each other out because of this alternating piece. But if we keep going, we'll see that pattern continues. For n equals 3, for every odd n, the sum doesn't survive. It cancels itself out because negative 1 to the third power is negative 1. But if we do one more, if we do n equals 4, we got x to the fourth over 4 factorial for f of x, and then it's plus a positive x to the fourth over 4 factorial. And then we can keep going from there, but only the even terms are surviving. So what's happening is that we got 1/2, this is x to the second over, actually here, I'm going to simplify that real quick. This term survives, this term doesn't, this term doesn't. This is x to the second over 2 factorial plus itself, so that means you have 2x to the seconds. Oh, sorry, first, I forgot this. This is 2. But the n equals 2 term survives. That's 2x to the second over 2 factorial. And I know you could simplify that. You could just make that be x squared, but we're keeping this and keeping the factorial so we can see a pattern without having to count out too many numbers. We have n equals 4 survives because that's an even term like we said. So there's 2 of those. X to the fourth over 4 factorial plus x to the fourth over 4 factorial makes 2x to the fourths over 4 factorial. And then it keeps going, every even number. So in math, we have a way of expressing an even number, right? An even number is 2 times any integer. So 2 times n, this will always be even. So what we're seeing for the series, and here maybe we can cancel out the 2's on top. If you distribute this 1/2, this is 1 plus x to the second over 2 factorial plus x to the fourth over 4 factorial. For this series, we have x to the 2n over 2n factorial. I'm plugging in, I'm saying this is 2n because it's always an even number, and I'm saying this exponent is always 2n because it's always an even number. And then to make sure this is working, we could test it by plugging in some numbers. You plug in n equals 0, then you have 1 over 1, which makes 1, just like it's supposed to. If you plug in n equals 1, then you have x to the second over 2 factorial, so that checks out. If you plug in n equals 2, that gives us the third part of our partial sums. Okay, so that is the new series. And you could apply the same process. Look at the partial sums. identify the pattern for f of x minus g of x down below. Sorry, one quick note, if you need help with this one, I made a substitution because I saw every power that was even was surviving. An odd power would be an even number plus 1. So this is how you could represent every odd number.